All right, let's get right into it. We are literally surrounded by AI that seems to learn like magic. But how does a computer actually learn something new, without a person sitting there programming every single rule? Well, today we're going to pull back the curtain and unravel that exact mystery.
I mean, really think about this for a second. You could try to write a program with rules, right? Like, if it has pointy ears and whiskers, then it's a cat. But what happens when the cat's facing away? Or it's a cartoon drawing of a cat? All those rules just fall apart, instantly. And this is the exact problem neural networks are built to solve.
And this slide right here, it just perfectly nails the huge shift in thinking. The old way was all about trying to predict every possible scenario and writing a rule for it. It was brittle. But with neural networks, we completely flipped the script. Instead of giving the computer the rules, we just give it data, thousands, maybe millions of pictures of cats, and we let it figure out the patterns all by itself. It literally learns the rules from the data.
So, what is the big idea here? What's the fundamental concept that's powering this entire revolution? Let's break it down.
So, at its heart, a neural network is a system that's inspired by our own brains. We've got something like 86 billion neurons all connected together. But instead of squishy biological stuff, the network uses pure math to turn an input, like a photo, into an output, like the word cat. And the absolutely crucial part is that it learns how to do this just by looking at examples, not by following a list of human-written instructions.
Now, it's really important to keep this in mind. That brain analogy, it's super helpful for getting the basic idea, but it's just an inspiration. The way you really want to think about modern deep learning is as a form of applied numerical optimization. It's an incredibly powerful mathematical tool, not a perfect copy of a brain.
So what does this learning process actually look like in practice? Well, believe it or not, it all starts with the network just making a guess.
This is it. This is the entire learning process in a nutshell. It's just a simple, three-step loop that the machine repeats, sometimes billions of times. First, it makes a guess. Then, it checks to see how wrong it was. And finally, it adjusts its own internal wiring just a little bit to be less wrong the next time. Guess, check, adjust. That's the whole game.
Okay, so that guess part, that's what's called the forward pass. You feed it some data, say the pixels from an image, that data flows through layers of artificial neurons. Each connection between neurons has a weight, which is just a number that signals how important that connection is. The signal ripples through the whole network until, at the very end, an answer pops out. And that first guess, it's going to be total nonsense because all those weights are completely random to start with.
Now there's a secret ingredient in here that makes all the difference. It's called an activation function. As this slide shows, without one, even a network that's 100 layers deep is no more powerful than a simple spreadsheet formula. But when you add this little piece of code, like the super popular one called ReLU, it basically lets each neuron decide whether to fire or stay quiet. And that simple on-off switch gives the network the power to learn incredibly complex, curvy, non-linear patterns in the world.
Okay, so making a random guess is the easy part. The real magic, the actual learning, happens in the next two steps, where the network figures out how to get better by learning from its own mistakes.
This is our check phase, and this is where the loss function comes in. You can think of it like a really strict teacher. It takes the network's wild guess, say, I'm 20% sure this is a cat, and compares it to the right answer, which is 100% cat. Then, it boils down that difference into a single number, a score, that tells the network exactly how wrong it was. The entire goal of training is to get that error score as close to 0 as possible. And now for the adjust phase. This is where the genius comes in. An algorithm called backpropagation takes that final error score and works its way backward through the entire network. It's like a detective retracing every single step to figure out precisely how much blame each and every one of those connections deserves for the final mistake. It's a truly brilliant piece of math.
This quote is the perfect way to visualize what happens next. Think of every possible setting for the network's weights as a single point in a massive mountainous landscape. The height at any point is the error, the loss score. So a high peak means a huge error, and a deep valley means a tiny error. The goal is to get to the bottom of the deepest valley. Backpropagation tells the network which direction is downhill from where it's currently standing, and that process of taking small steps downhill is called gradient descent.
Now, as it turns out, there are a few different ways to walk down that mountain. You could look at your entire dataset all at once to get a perfect, exact direction for downhill, but that is incredibly slow. Or you could just look at one random example at a time.
That's super fast, but your path down the mountain is going to be really noisy and erratic. The Goldilocks solution, the one that's used pretty much everywhere, is the mini batch. You look at a small group of examples, get a pretty good estimate of the slope, and take a step. It's the perfect balance between speed and accuracy.
But of course, modern deep learning doesn't just blindly walk downhill. We've developed some really sophisticated techniques to navigate that error landscape way more efficiently. It's all about training smarter, not just harder.
These advanced techniques are called optimizers. Think of them like high-tech hiking gear for our trip down the mountain. Momentum is like rolling a heavy ball downhill. It builds up speed so it can cruise right over little bumps and flat spots. RMS prop is more like a cautious hiker who automatically shortens their steps on steep parts and lengthens them on flat parts. And then there's Atom, which brilliantly combines the ideas of both momentum and RMS prop. It's so effective that it's become the default go-to optimizer for almost everyone in the field today.
Now, the single biggest danger you face during all this training is a problem called overfitting. The best way to think about it is like a student who doesn't actually learn the material for a test, they just memorize the exact answers on the practice quiz. Sure, they'll get 100% on that specific quiz, but give them a real exam with slightly different questions and they'll fail completely. An overfit model hasn't learned the general pattern, it's just memorized the training data.
So, how do we stop this from happening? Well, we have a whole toolkit of tricks. We can add a penalty to the network for getting too complex, which is called weight decay. We can also just watch its performance on a separate set of data and stop training the moment it stops improving. But one of the most clever ideas is called dropout. During training, you literally just randomly turn off some of the neurons in each step, as if they'd called in sick for the day. This forces the other neurons to step up and learn more robustly, so the network can't rely too much on any single connection. It's a simple idea, but it's incredibly powerful.
So we have our core loop: guess, check, and adjust. And we have smarter ways to train and avoid pitfalls. So let's see how these fundamental ideas scaled up to create the absolutely massive AI models we have today. This timeline just shows you the insane acceleration. We went from early networks in the 90s that could recognize handwritten numbers to AlexNet in 2012, which basically kicked off the entire modern AI boom. Just a few years later, ResNet let us build networks that were hundreds of layers deep. And then, in 2017, the transformer architecture arrived and completely changed the game. The key breakthrough in the transformer is something called the attention mechanism. You see, older models had to process a sentence word by word, in order. But attention lets every single word look at every other word in the sentence all at the same time and decide which ones are most important. This ability to process the entire context in parallel is what allowed these models to be scaled to a size nobody thought was possible, and it now powers pretty much all of the state-of-the-art AI you see.
And this number, this is the result of that scaling. A big model like GPT-3 has over 175 billion parameters. Every single one of those is a knob that gets tuned using that same simple guess, check, adjust loop we talked about. It's just that the loop is repeated billions upon billions of times on a truly colossal scale.
So, there you have it. We've gone from the simple idea of a single artificial neuron to massive networks with hundreds of billions of them. And all of it, every single bit of learning, is driven by those same elegant principles. Make a guess, measure your error, and adjust yourself to be a little bit better next time. That simple loop, scaled up, has unlocked abilities that we are only just beginning to comprehend. Which leaves us with the biggest question of all.